Hello and welcome. I'm Shadow of Shadow Gaming, bringing you Programming with Shadow, episode number 69. So in today's lesson, we're going to be refactoring the AVL tree we did last time a little bit. So we'll do a little bit of cleanup, and I've actually thought through the implementation a little bit, and we'll see if we can't get it a little better off than we did last time. So we'll go ahead and hop right in with our nodes. So I thought about it and what I was trying to do, and I can't think of anything that I want to do there. So what I'm going to do instead is going to add a public int height here. So we'll just add our height here, and I'm actually going to make these properties instead of variables. So we're going to do it like that. Now, let me go, let's see, we will come over here, and we're just going to delete the tree node class. We don't actually need it. All right, so that broke some things. Let's go fix what we broke now. Let's look at tree printer. So this one, we need a print method. It takes the tree. It's still good. So let's make some adjustments to the string here. So we have a new string, root value. Then let's do something here. Let's make this a right instead of a right line. So now we'll write out that method, and now if we're adding anything else, now we'll do if root.height is not null. So if it's not, so if there's a height, then we'll do console.write root.height balance height. What I've done to get us all off track that quick. Get balance, passing in root. And close, put it in there. Get balance is taking AVL tree root. We'll fix that in just a second. So now we want to finish the line, so we'll do console.write line. And there we go. I think that'll do what I wanted to do. So let's see. Print in order takes a tree node. I think that's still good. So now we can delete the two AVL special classes. And let's do this one. There we go. And we're done. So what we did, we got rid of we combined the 4 special case methods into 2 more general purpose methods just by removing the tree node and AVL node distinction. So for that, we added if there's a height, then we display the height and balance, because the balance requires heights. But if it's not available, we just don't print it, and that should keep the BST safe from the AVL tree. All right. Go to the BST visualizer. Let's make sure it's still fine. So this one, nothing broke, so it's probably actually good. Let's go look at binary search tree. And let's rename it. Binary search tree. There, when I press Control RR like that, it renamed the file as well. So now the file's been changed, and it should have fixed the program also. So yes, we're now calling it a binary search tree there. I'll leave that as BST, but probably could rename that as well. So let me see. I don't think there was anything here. Yeah, I don't believe I changed anything here actually. Did I optimize that any? Nah, I don't believe I did. Okay. All right, so binary tree is done. So let's look at the AVL tree now. So this one is broken all over the place. So let's go ahead and start fixing it. So first thing here, all these tree nodes. So everywhere that it's got that, I'm going to press, let's see, Alt, Shift, semicolon, select them all and change them to tree node. There, that fixed almost everything. Extra usings. All right, so let's see. So update height. Still good. I don't think I had to change anything here. So I think the first one's rotate right. So let's adjust the nullability here. So y equals left. So there's a hard requirement here. So if this is null, it's going to everything breaks. So let's add a new invalid operation here. Left child must not be null. So there it's on the implementer to make sure that condition's right. And that makes it so this one's no longer nullable. Which means X is no longer null here. Right. I think that's not the case. I think the analyzer is wrong there. Here, let me expand this just a little bit. So what this is saying is if y left, x gets whatever is in y left unless it's null, and then it throws. Here it's saying y or x could be null here, so it's saying you should do that. That's not correct though. Right could be null, but not x. I think the analyzer is wrong on this one actually. Let's see if we rebuild if it changes that one. I don't know if it will. It does not. Oh, I guess maybe it's this one. There. Okay, I was saying it, so there. So T2 on the other hand, it can be null. So that's one of the cases, the rotate right, that's what it's actually concerned with, is the right child. So it makes sense for left child has to be there, right child could be there. And update height is fine either way. So rotate left, it has a similar changes. So this one's not null. This one is not null. Throw invalid, operation exception. Right child must not be null. Throw new invalid operation exception. So now this one's not null, and this one's not null, and there. All right, so there's this little cleaner, so handled the nullability properly this time. So let's see, anything else? So we can remove an extra line there that I've added at some point. Check these, the methods look all right. So balance still looks all right. So one thing I noted here, I did the checks on the outside. I looked at it more closely. I think this would be actually a little clearer. let's do it like this. So if balance greater than 1, so tree node left equals node.left, or throw new invalid operation exception. Left child expected when balance is greater than 1. So that's the exact thing the balance is indicating. So if we look at get balance, so if it's a 1, if it's greater than 1, there's a left child, so this one's bigger. If it's greater than 0, there's a left child. If it's less than 0, there's a right child. So that's what we're actually the condition here. So this shouldn't be possible based on our balance condition. So left AVL rotation. So now that simplifies the check. So now we can just do if value is less than left dot value, return rotate right, passing in node. Here we'll clean up the implementation. So there's that one, and then we just have to check the other condition, which is this one here, by the way. So let's copy this. So left right. So if the value is greater than left dot value, that can be left. We no longer need to do node left because we're already extracting out the left. And let's see, I made sure this was correct, so I was wrong on the first swap. So this is, you do a left rotation and then right rotation first, which is LR, which makes sense. And that handles the left case here. The right case will be very similar, just the opposite directions. So if balance is less than -1, then tree node right equals node.right, throw new operation exception, right child expected when balance is less than -1. And then we can grab the right rotation here. And we can grab this one here as well. There we go. So now we can remove this. We can make this to be just right. We can remove this. We can make this be right. And there. So now the upper part here, what we just wrote, these two lines are the same as these. So let me zoom out just a little bit so we can try to get them both on the screen, and that's not going to happen. Let's do it like this. Duplicate. There. So now we've got the new and the old styles there. So the old look like this. So each one we do the balance, and then we do whatever side it is. Here we just do the balance checks and then do the inside one. So I'm arguing that these are equivalent. These I have warnings that these could possibly be null, and we could fix that, but we'd have to do it otherwise. Here we're handling it here ahead of time, so I guess we would just do it here. So I would argue these are about the same, so you could pick which one you like better. I like this one because even though it's more nested, because the conditions are clearer, there's only one condition each. But I would argue there's not a lot of difference, so you could take your pick on them. I'm going to update it to the new one though, because I like, after thinking through and looking at the design a little more, I think that's the one I would lean toward. All right. So that takes care of that method. Search is good, I think. If value equals value, node value. Yeah, I believe that's fine. So the other one here was delete. We haven't done delete yet. That was what we're going to work on. So probably next. So I guess we can go ahead and just start with delete. So delete's a little bit of a bigger method. Here, let's go ahead and enable it. So when you work on a delete, there's a few steps you need to follow. So we will do, let's write down the steps here. So we need to, maybe not. We'll just go from this. So the first steps, we need to identify what we're deleting. And then we need to do the delete. Then we need to update the height. And then we need to rebalance. So we'll see it does a lot of this up here that I just redone up here for balancing. If we're going to copy that down for to do some rebalancing on the other side. So let's begin. So first things first. First things first, we check for our null, just like we've done for the rest of them. Give it a couple spaces, so that's good. All right, so now we'll do the rest of this. So here, if it's less than value, we go left. We still do that. Search still works exactly the same. If it's right, we go right. Else, they're equal. And here we do, we have a case for no children, which is still the same. One child, which is still the same. And then two children, which is still the same. So this so far so good. Now though, we're going to reach part 2. So now we're going to need to update the height. We have a method for that, so we can just call update height on node. So now that updated all our nodes. So now we need to rebalance. So let's begin by getting the balance. All right. So when we do the rebalance, what's going to matter is which subtree is bigger, the left or the right. So if the balance, so same as before, if balance is greater than 1, so if it's bad on the one side, we'll do what we did a minute ago. We will do basically this. Let's just grab both of these. We'll grab both of them and just copy and paste them. All right, so if it's left heavy, we'll grab the node. Then we're going to do something interesting. We're going to do int left balance equals get balance factor of the left tree. So we need to see what its balance actually is. So now this if condition becomes left balance greater than or equal to 0. Rotate right. So notice that's not the same thing we did before. I don't know if it's a left rotation anymore, not either. I don't know if that's the right designation there. So here on the other side, there's no check here. So the conditions are if it's greater than or equal to, we do that. where did I just go? I've got all kinds of wolf messed up there. Yeah, all kinds of messed up. Here, right. Let's put that in braces because I don't like the look of that one somehow. All right, so there. Notice we don't do the full left-right rotation. There, I think that one's not right. So now if the balance is greater than or equal to 0, we rotate right. So if it's heavier on the left, we pull the right side up. So if we have a so if we have this structure A, B, C, here, we don't want to do that. That's the result. What we're doing is say we have CAB. Say we have something like that. What we're doing is we're rotating to the right, so C goes down and A comes up. That's what we're doing here. So that's this condition. So we need to do the opposite of it's the. Wait a minute. Rotate left, rotate right. Yeah, I believe that's what we want. So if it's the other way, we want to do the opposite. So we'll get the tree, we'll get the right balance. Now, let's just delete this since it didn't help out before. So now, if right balance is less than or equal to 0, then return this one will be the opposite. So this time we'll go left, and else we'll do node dot right equals rotate right, return rotate left. That should get us a balanced tree. So let's do some additions and let's see what happens. So let's run it. Let's do some tests. If we insert, let's do T. Numlock isn't on. So let's do insert a 10, insert a 5, insert a 15. So now we've just got a real basic tree. So now if we delete 5, do 3, 5, there we go. They're handled a leaf fine. So let's try it again. Let's do 10, 5, 15, 12. So now we've got a little bit heavier on the right side. So what happens if we delete one child? We'll delete 15. And it just pulls back up. So that seems good. So now if we have 2 children, let's try that. One, so let's do, we'll change the order up here. We'll do 20, 10, 30, 15, 25, and 35. So now we've got a full tree. And let's delete the root, so one with two children. So now 25 comes up and everything rebalances around it. So all the conditions at least seem to work. So we should do a rotation. What we can do, let's do this. Let's add a few logging statements here. So we'll do a CW performing. Which one is this? Right balance RR rotation. We'll do that here as well. Performing RL rotation. So this one will be performing LL rotation. CW performing LR rotation. All right, so now let's see what that does. So then we'll try a little case that should trigger some rotations. So one, we'll let's insert 30, 20, 40, and 10. Now we will delete 40. So that'll make it a linked list, so we have to rebalance. And deleting, removed the leaf node, and then we had to rebalance after we removed the leaf node, and we got that. So yeah, let's do it. Since we added the debugging, let's do that last case as well. So we'll do 1, we'll add a 20, we'll add a 10. I don't remember what other values I did. I had a pattern. 15. 25, I guess, and 35. Yeah, there's just a full tree, and it's at least sort of balanced. So now if we delete the root, there, find successor. There's two children, so the successor is 25. So then we go left. We found that. We deleted, and then we removed the leaf node. Notice there was no rotation, so no need to rotate there. So everything still fell in a relatively balanced tree. If we remove 30 now, there, one child promoted right, we're still okay. If we remove 35, 35 removed. So now we had to perform another LL rotation. Left. So that's pretty much an introduction to AVL trees and work with them. So the benefit an AVL tree gives you is it's a little more balanced. It's a lot harder. We're not getting a link to list out of it. We're keeping more balanced. So the make sure I don't have anything else I wanted to mention. Yeah. So that's pretty much an AVL tree. It's trying to help you balance a tree. So you have to keep doing work to it as you insert and delete to make sure it stays balanced. But doing so, you get good search properties. So search is good. So let's see. I'm looking for something really quickly. there. So big O complexities. So in the worst case, search, insert, and delete all end up being log in this case. So at worst, you're just finding how big they are, and it's going down a logarithmic path. You're no linear. We're not going down a linked list. So in the average case and worst case, you're getting similar performance. That can be useful, and we'll see. Probably the next tree we'll look at. There may be one lesson in between because I'll be on vacation, so do a light one instead. For the most part, we'll see that AVL tree and the next one, red black trees, they do it in different ways, but what they're doing, they're trying to balance the tree, trying to make it easy for you to easy for your searching and inserting and everything. The advantage of AVL tree is it does a pretty good job of keeping everything balanced. The next tree, like I said, next one's called red black tree, so it doesn't do as good a job, but can be a little bit better for insert. So worse search, better insert, I believe is how I've always heard it. Other than that, I think that's pretty much all I wanted to cover on this. So we did a little bit of cleanup, and then we added the delete case, which we didn't have time for last time. So yeah, I think that'll do it. So we'll go ahead and call it with that one. So thanks for watching, and have a wonderful rest of your day.